She received her BTech from IIT Madras in 2004, and then she got her PhD from Cornell. So I'll turn it over to Anima.
Thanks a lot, Ravi, and I apologize I couldn't be here for the whole workshop, but I heard there were a great set of talks. I looked at the schedule, and it was great to see a breadth of topics. So today I kept the title quite broad because I thought I would cover a whole range of recent topics in machine learning I've been thinking about, but more, emphasize on how theory and practice could possibly meet together, right? Because historically there has been quite a big gap. Now with the advent of deep learning, there is a sort of disruption, right? So traditionally the theory has been for convex optimization, linear models. We can go into depth, we can give all kinds of guarantees, but the models that are now being run in practice is with deep learning, and that's highly non-convex. We don't understand the landscapes. We don't understand the generalization. So how do we reconcile the two? I think this is something as a field we are grappling with, right? And so I'll show some works that try to address this. And before I get into each of those topics, I want you to think broadly when we say machine learning, what are the three facets, right? So when we are thinking of the theory, we mostly think of the algorithms, right? So we think of computational complexity, sample complexity, like what does the algorithm do? But when it comes to practice, the other two facets are equally, if not more important. In most practical applications, data will be a big barrier. So the kind of modern machine learning is mostly supervised learning with labeled data, and we always don't have lots of labeled data. So how do we collect the data and process it in the right way is very important, right? And then the other part is the infrastructure, how to productionize machine learning at scale. How do we grapple with changing data that's coming on, or how do we grapple with growing number of customers that need to be served? So all the side from the systems details to the hardware to scaling up, those are important as well. Right, so it's important to think of all these three facets together in a unified way, and we usually don't do that when it comes to theory. And that's because for theory, we like our problems to be nicely defined, simple enough that we can understand the intuitions. And the hope is some of the times that will indeed carry through, right? The simple models, even what you derive for a linear model, could hold true for deep learning models in some of the settings. But the question is when, and that's important to kind of get a sense of that. And so that's kind of the broad overview. I want you to think about how we not only think of algorithmic analysis, but we also think about data, and we think about scale, and we think about how to build the machine learning stack. So how we can think all of that together is what kind of my research has been aiming to do for the last few years. For instance, when it comes to data, right, so in academic papers, we mostly look at benchmark data sets because we can compare easily with the other works, and that's how we can produce a scientific work, right? But in practice, usually there's hardly any data to begin with. You have to collect the data. And so the question is, how do you collect this effectively? How do you aggregate the data effectively? So aggregation comes if there are many different sources of data or many different labelers of data, right? So they could have different kinds of label noise. How do you aggregate that? And then how do you augment your current label data? So in practice, especially in computer vision, augmentation usually means you crop, you rotate a bit, you do very simple changes to your image in the hope that it will prevent overfitting. But then what about much more sophisticated ways to augment your training data? Right, so you could do that if you have both labeled and unlabeled data. We have semi-supervised learning. So you can ask, how should I do semi-supervised learning efficiently? Or I could have domain knowledge. I could already, we already know existing physical models. We already know so much about the world around us. So we don't want to learn from scratch, right? So whereas deep learning, the way it is today, is kind of black box, learn everything from scratch. But if we have some knowledge and some data, how do we put that together? That's an interesting question. So those are the three facets of data that I want to think about, how to collect it effectively, how to aggregate it, and how to augment it. And then when it comes to algorithms, right, the core of machine learning is optimization, right? So we are optimizing a certain loss function. So how can we understand this non-convex optimization? That's something we need to understand much better than we are today. And then the other part is scale, and that interacts with infrastructure. So if it's no longer feasible to do optimization in a single processor or a single GPU, you want to now distribute it across multiple processors or even multiple machines across the network. How do you do that effectively, right? So there's both computation and communication costs. How do you balance that? So scalability is something we need to worry about when it comes to algorithms, and we need to worry about parallelization. So many of the algorithmic analysis, when we are asking of computational complexity, we are thinking of serial complexity, right? That's the traditional way of thinking. But hardly any of the machine learning is run on CPUs anymore. It's now a lot more on GPUs, and the gains are tremendous. And so we want to ask, what's the parallelizability of different algorithms, and how can we analyze that? And how does it interact with different kinds of hardware? In other scenarios, we may have hardware on embedded systems that has limited power, right, limited capabilities. So how do we do that? So those are all the questions I want to think about when it comes to scalability. And the third aspect my research looks a lot into is how to think of multidimensional processing. By that I mean go beyond just matrices and linear algebra, right? So even though our deep learning systems today are highly nonlinear, they're made up of extremely simple functions. You're doing linear algebraic operations in every layer and some simple nonlinearity, and you're composing that. But can we be much more intelligent? Can we now go from matrices to tensors, which are higher dimensional objects, and they can give us better neural network architectures, networks that generalize better, that are smaller and more compact, that could predict better. So how can we intuitively think of these properties through a tensor lens? So that's something I've looked at both from the traditional probabilistic models viewpoint, but also the deep learning viewpoint. And when it comes to infrastructure, as I said, one aspect is how to theoretically, use the knowledge of infrastructure to analyze the algorithms better, right? The other is practical, like how do we build the software stack that's effective? Like how do we ensure it's modular, it's easy to use? I mean, a large aspect of this deep learning revolution has been democratization, like how we can reach out to more people. These algorithms and math may be complicated. Not everybody can understand the details of it, but they could hopefully use them, right? And for that, you need like software frameworks. There's TensorFlow, there is PyTorch. There's all these frameworks that have made it easy for people to start building these models. And then you need like a platform. You need a place where you could bring in all the data, you can do all these frameworks, you can do inference, you can visualize, so all these, by each one by itself may be easy enough, but to put them all together for a system at scale is a big engineering challenge. And then at the last layer, I think of it as an application level services, and this is meant for enterprises or people with no machine learning background, right? So think of it as, you just send in all the images, you want the final answers, right? You want the text processed. And we are getting there, but we are not still fully there, right? And that's because machine learning in the wild is extremely challenging. we can train the models on some limited data set and you don't know what to expect at test time, right? So if you have to be an application level service, you should be able to handle any kind of input and you should be able to auto scale. Suddenly you have now a much larger amount of traffic you should be able to handle, and you should be able to adapt. So these are all things we still haven't even designed the algorithms very well, right? So think of it as, in the broad picture, an automated ML that does everything from hyperparameter optimization to adapting to domain shifts to non-stationarity, all these issues that would be done automatically by the algorithm. And we are not there yet. In fact, we are quite far from that. Right? But that's the utopian ideal where we can pretty much automate AI and serve it across many applications. So that's how I think of the software stack for machine learning. And I used to be at Amazon Web Services, so there we built several layers of the stack, and now at NVIDIA as well. We have platform, for instance, I'll show you later, for Drive and many applications that have this philosophy of a modular nature. And so to me, like kind of thinking of the engineering side and interacting with the engineers and then thinking of the theory, right, how the two connect, that's very important. Because I think the main takeaways from my time in industry has been, first is not just to focus on the theoretical complexity of algorithms, right, and definitely not just the serial complexity. Try to think beyond that. And the other is to focus more on the data aspect. There isn't much research being done on how to more effectively collect data and to learn with less data. So that's something we want to focus more on. And that, I think, would have great practical impacts. So that's my overview. And since this is a small enough audience, I like it to be interactive. So before I jump into the topics, if you have some high-level questions or even comments, I'm happy to take them.
Moving from matrices to tensors, what does that buy you exactly?
So I will go into the details, but the main intuition is you have a much larger space of computations, right? So think of matrices you can only multiply in two directions, or technically it's only a linear operator, so its range of operations is limited. Whereas with tensors, it's a multilinear operator. You can contract the tensor in many different dimensions. And so from that range of operations, you're getting more effective reduction, right? Because, you can always convert a tensor to a matrix, right? So you can always flatten it and make it a matrix and do a matrix operation. But that means you're throwing away that information. And that's what we want to preserve. And so I'll go deeper into that later in the talk. But that's the high level. Neurobiology, yeah. That's a even harder question, right? So, because right now the optimization and even the architectures, everything is quite removed from how it's in the brain. We can have, I think there's high-level philosophical connections between the two, but not the actual details, definitely not the optimization algorithm. And there have been a few attempts to try to bring in Hebbian type of learning or other type of learning from neuroscience, but they haven't been very effective with the current machine learning algorithms. And for me, that may be due to two reasons. One is we still don't understand the brain very well, right? How it learns. Maybe it's not just the Hebbian rule. There may be so many other mechanisms. And the other is, given that the architectures are so different from the brain, maybe it's not the same kind of algorithms that would be effective. So the data collection, if you ask in practice, it's really done in a pretty inefficient way, right? So in most companies and even research labs, it's usually like, okay, either I go to Mechanical Turk or I will take a vendor and then forget about it. Like you can maybe specify some categories. You say, this is the kind of data I want. This is the number of data points I want. And either you can like scrape the data from the web, right? The unlabeled data and then have it labeled, or you can ask somebody else to do it. But collecting in this way, first of all, highly biases our data. I mean, so there's the other aspect of algorithmic bias because, if you look at face recognition, there's been a lot of work that's been talked about how it doesn't cover all the demographics, all the age groups, because celebrities are very different from the human population across the world, right? So that's one challenge by not thinking how you're collecting the data diversely enough, you're limiting your training data. And the other aspect is, the machine learning scientist is not actively thinking about that, right? It's usually people with almost no machine learning background who are doing the data part. There's usually a separate data team or a separate vendor. And I think that kind of lost connection is what creates a lot of bottlenecks in practical machine learning groups. From what I've seen, many times you would have to go back to the vendors and say, no, this was not the right category, or I misspecified it, or I realized in this kind of specification it became highly biased, right? So this back and forth now takes months or even longer because there's not a seamless connection that makes it possible. So active learning can solve that, but we don't have currently systems that can do it very efficiently. Great, so now I'll dive into some of the topics, and again, I'll give you some snippets. So what I'll do is give you the main theoretical results and some intuitions, and also what we are observing in practice. And so this way I hope to cover quite a few topics, but I'm happy to dive into some details if you're interested. Yeah, so the first work I want to cover is what I call SIGN-SGD, which is compressing the stochastic gradients to just their signs and asking what is the impact that's going to have in the non-convex settings. So this appeared at ICML this year, and also another paper accepted at ICLR for the coming year. And the question is, why bother with gradient compression, right? So this comes into picture when we are doing distributed training. When we are doing distributed training on limited bandwidths. So think of it as the simple form of parallelism is the data parallelism, right? So if I have two GPUs, I'm going to divide up my data into two parts. And similarly, as many processors I have, I can divide up my data and give that part of the data to each processor. And so the mechanism is it'll process its own mini batch of data, but you need to aggregate all of them. So there are, again, different communication topologies to aggregate that data. The all reduce is where everybody communicates to everybody else. Then there is the parameter server where there is a central server where this is communicated. Right, so this parameter server could be actually fragmented. It could be on multiple machines, but as a concept, it's this server, right? So it need not be one machine that does this, but conceptually there is a server framework that can aggregate all the updates in the parameters. And so now this is a communication-heavy task, right? So the amount of communication will depend on our size of mini batches. So if you have small mini batches, you have to communicate more often because you're only computing the gradients of a small batch, and you have to immediately communicate and aggregate that. And larger mini batches, people have tried, but there are challenges in generalization. So there is limits to how large the batch size can be in any application. With vision, it tends to be much larger than language. Language even tends to be very small mini batches. And so that's the major bottleneck. If you could just do, of course, everything trivially in one shot, you would just communicate once. But that's not possible. You have to chunk up your data to mini batches and compute in mini batches, right? So that's the challenge. And so that's the question of how to compress this what would be the impact of compression on both the settings, on both the directions, both when you're sending it to the parameter server and sending it back from the parameter server. And so what we proposed was a very simple scheme where you have compression in both the directions to just a single bit. Right, so for each parameter, you just take the sign of the stochastic gradient and you communicate it to the parameter server. And the parameter server now takes the majority rule because you still want it to be a single bit. Right, so traditionally, this would be just the full precision gradients, and this would be the average. And now, instead, we are replacing it with the signs in both directions. So some of the earlier works did this only in the one direction, and they all reduced. So they didn't get as much gains as us because we are now doing it in both the directions. Yeah, and so now the question is, what is the impact of this, right? So it looks like we're doing severe compression. What can happen to the optimization landscape by doing this? So, yeah.
Small question. When you say parameter server, which is the corresponding hardware component? Say, are you referring to the CPU memory or GPU memory?
So that could be anything, but in practice, it tends to be the GPU itself because going back to the CPU is expensive. So think of the parameter server, in fact, as fragmented across different GPUs.
Right.
But that's where the aggregation happens, right? So that's the...
But in that case, I mean, finally, when you aggregate the, say, for determining the sign, you come back to CPU memory. Otherwise, say, I have...
No, everything happens in the GPU itself.
But I have, say, 4 GPU servers.
Yeah.
Then memory is also, there are 4 GPU memories, right?
Yes.
So individually they are updated if we use them as parameter servers. But finally, I mean, this part, how is it determined?
So this part, you mean like, I mean, if depends if these GPUs are within the same board, right? It doesn't have to go through the network. You don't need to come to the CPU. If it's across different machines, then yes, it has to go through the network.
Okay.
So, but that's a detail. You could run it either way depending on what the hardware configuration is.
Okay, thanks.
Yeah, so that's the algorithm, and now we can ask what is the impact, right? So in the first work, what we did was the large batch analysis where we said the batch size is asymptotically going, it's tending to infinity. And then in a follow-up work, we also have the finite batch analysis. So let's first look at the large batch analysis. So these are the assumptions. I think they are pretty mild, as you can see, right? So you want to assume that the function has a lower bound, right? So that's kind of, I mean, the loss function should have a lower bound. Otherwise, you don't want the minimization to just go to minus infinity. Then there's some variance, right? So usually you think of the variance that's the upper bound on coordinates, but if you have the coordinates-wise bound, that could be a sharper bound. And the other is the Lipschitz, gradient Lipschitz constant. So this is again the standard smoothness and noise bounds. These are standard in any optimization analysis. And what we want to ask is, what is the rate of convergence for just full precision stochastic gradient and then the sign stochastic gradient, right? So, and this is first order convergence rate, right? So when we are saying an expectation, how is the norm of the gradients, how is that vanishing, then that's only first order, right? Because we are only thinking about the gradient and we are not asking the second order conditions. In some of the other works, I've also thought about second order and how saddle points escape when all those questions happen. But in this work, we said mostly we want to first look at the first order, right? So how fast does the gradient come down, and that's what will give us the convergence rate for our training loss. And so the question here was, what you see here when you compare the convergence rate of SGD and SIGN-SGD is that it's a different geometry, right? So here it's an L2 rate, whereas for SIGN-SGD it's an L1 rate, right? And that's kind of intuitive why this is L1, because now you have to ask when do the signs get wrong? Like, when are the signs wrong from, the sign of the stochastic gradient is wrong compared to the sign of the true gradient. And so it's a different geometry. And the key thing in this work was for us to analyze it differently rather than in the previous works, which tried to correct for the quantization error and try to argue that it would follow a similar trajectory as the stochastic gradient itself, right? So that's what the previous works did, and we said, no, that's not actually necessary. I mean, this is a different algorithm with a different trajectory, and that's okay. We can still analyze the convergence rate of this. And so that's what we found here, that without any further assumptions, it's hard to say which one dominates the other. In fact, you can come up with conditions when one is better than the other, right? And a slide later, in fact, I'll give you some of the examples of when SIGN-SGD would be bad, right? So, but what are the good conditions? So when it'll be good is when, essentially this happens, right? So if the gradients are dense, then you have this L1 to L2 conversion being like with this root D factor. And same here, if the smoothness is also dense, then you have the similar conversion here, and similarly the noise is dense. So if all these quantities are dense, then you have the same rate for both SGD and SIGN-SGD. And so that's what our theory is saying, and so we can then verify in experiments to see, in many standard empirical experiments, is all these quantities, are they tend to be dense, or will there be some sparsity, right? So, but that's the intuition. You can get the two rates, and you can also ask when they have a similar rate of convergence. Any questions here? Yeah, so that's the result, and now, and that's what I meant by this density, right? So you can ask, in practice, how does the density look for various quantities? So we have the more detailed results in the paper, but what you can see is it's actually quite dense. It gets pretty dense, especially as the training proceeds. So the variance you see is, pretty dense, and these are for different algorithms. So Signum is essentially our SIGN-SGD algorithm, but with also momentum. So we also added the momentum term before taking the sign, and that's the Signum algorithm. And so that's what the practice says, right? So the theory is saying you can expect the same convergence rate for both SIGN-SGD and SGD when these quantities are dense. And in practice, we find that that is indeed the case in many experiments. And so that's means that SIGN-SGD could work very well in many of the empirical settings. And so that was just for one machine. So if you just had no aggregation in the way back, right? So it's just one, take the sign and look at its convergence rate, you will get that. But now if I have multiple machines, I have to think about the aggregation as well. Like, what is the impact of aggregation of signs from different machines? And then we need an additional assumption, and this actually gives you quite a bit of intuition also of when SIGN-SGD fails. So what this assumption is saying is that the gradients should be unimodal and symmetric. So the distribution of gradients should essentially not be very skewed in one quadrant versus the other, right? So you, if you can hope for unimodality and nearly symmetric gradients, then you're in good shape, and then you will get the variance reduction with the number of machines as well. So if m is the number of machines, you can get 1 over square root m reduction in your variance as you add more machines. Because that's the idea of adding more machines, right? So if you add more machines, you want your variance to reduce, and the best rate you can hope for it to reduce is 1 over square root m. And we can obtain this rate when we make this additional assumption of unimodal and symmetric gradients. So intuitively, why is this very important, right? So think of it as like if there is noise that is skewed in in only one axis. Let's say in the positive axis, you have a highly skewed noise. Then the sign is very wrong compared to the full precision gradient, right? So the sign is impacted a lot more by this skewed noise. But if we can avoid this, then we are in good shape. And there was a paper in ICLR last year that won the best paper award about Adam failing, like when does Adam fail? And that was also about skewed noise. And Adam is actually in the limit just this SIGN-SGD because if you just take one window of it, it's the same. That's a detail anyway. That's a tangential result. So don't worry about it if you are not aware of that. But there's also connections with some of the other works on optimization that have been recently, people have been talking about Adam. But yeah, so that's the idea. Like, if you can hope for these gradients not having any kind of skewed noise, then you can expect to have a good rate even as you add more machines. Because that's the purpose of adding more machines, right? You would like to, or processors, you would like your variance to reduce. And this is what we found, for instance, in ImageNet and many other experiments. We did find that the gradients are indeed unimodal and symmetric. And yeah, so we also added a mini batch analysis in the ICLR paper. So don't worry again of all the details, but just pay attention to the result. This is now a sort of mixed norm. I mean, earlier it was just L1 norm. This is both L1 and L2 norms that are mixed. But you can still get a convergence rate guarantee even if you have a finite-sized batch, whereas in the earlier case, we felt like the large batch analysis was not a good assumption, right? Because in practice, we don't run our batches to be very large. So that's something we wanted to overcome, and we did that in the latest works. So again, the details you can refer there, but the main idea is you can also get convergence rate guarantees for the finite batch setting. And so what is the main intuition of why all this works, right? So why is SIGN-SGD even working? So think of it as when you are in the large signal to noise ratio, meaning your gradient is quite large, the signal in your gradient is quite large compared to the noise. So that means you're still very far from your stationary point. So in this case, even if you just take the sign, you're making a descent, right? So you're making a descent in terms of your loss function. And that's what matters. So when you're in the large regime, you're making progress. And the hope is as long as when you are reducing your gradients, you shouldn't increase your noise, right? So as long as your signal to noise ratio overall is reducing, you can hope for convergence. And that's what we find in practice happens, that the signal to noise ratio actually comes down as you're doing the training, right? So you need this for convergence. Without it, you cannot have convergence. Because ultimately, you want your gradients to go to 0. And for that, if the noise overwhelms and noise tends to be very high, you cannot shrink down your training loss. Of course, here I'm not talking about generalization. That's a whole other issue, right? You don't want your training loss all the way to 0, which is another whole other question. But that was the intuition again, because here we actually have this, what we call a critical signal to noise ratio in our theory. And the intuition is as long as all of these, all the coordinates have their gradients go below the signal to noise ratio, you can have convergence, right? Because everything will ultimately shrink. And that's what we find in practice, that it's actually happening. And so that's the main intuition, like you actually don't need the full information in your gradients, because in the large signal to noise ratio regime, all you need to do is make a descent, right? So as long as you're making progress, you're good. And SIGN-SGD ensures that as long as you don't have highly skewed noise or all these other bad scenarios. And so that's what makes it work in theory.
The earlier theorem, and then also this symmetric noise theorem, are they, did you have to develop new tools, or is it sort of like the Robbins-Monroe style analysis? Or?
Yeah, so I mean, the concentration bounds are pretty much like, there's the Gaussian tail bound, and there's a few things we borrowed. And so, yeah, so we didn't develop any new concentration bounds, but the idea was, the new aspect was to directly analyze this algorithm rather than trying to correct for the quantization error, right? So all the previous algorithms said, when you quantize, try to make corrections to your quantization error because your gradient estimate is biased. Because then you can try to follow the same path as SGD, whereas we said, no, let's do a different analysis where we don't correct for it. Instead, we analyze what is the probability of you getting the signs wrong, right? The sign of the stochastic gradient, how does it differ from the sign of the true gradient? And so for a single machine, it's just one random variable, and that's easy. But for multiple machines, now you have this binomial variable, right? Because you need to think about signs of all the machines. And that's when it gets more complicated. But we are actually thinking of some new concentration bounds that'll be needed for some of the Byzantine fault tolerance extensions we are thinking of. So I think there's also room to think of new concentration bounds here.
So if you have one bit, then you get this these results, and also this 2 over square root 3 constant. Is there a trade-off, like if you increase from 1 bit to 2 bits to 3 bits, do you get like the constant changing? Can you get it?
I mean, if you even think of the simple setting, right, this is just the one worker SIGN-SGD large batch setting, it's much simpler. I mean, the main issue is if it's not the sign, it gets more complicated because, if it's a sign, you can just, it's a Bernoulli random variable, you can easily analyze. Now, if it is some other categorical variable, how does that relate to your original continuous variable? I think that's a harder one. But in principle, you can, right? Because instead of this, we were thinking of this unimodality, and now it's only the positive and the negative side, but now instead you have other quantizations, so you want to worry about all those bins. Because here there are only 2 bins, the positive and the negative bin. So I think the analysis becomes a lot messier. In principle, it's fine, yeah. Any other questions? Yeah, so that was the theory, and now in practice, so we have the PyTorch implementation that Jave, who's in fact still an undergrad, he built it from scratch, and I'm very impressed on how he did that within a few months. And the idea was not just to get it to train well and to have a good test accuracy, but also look at the compression rates, right? Like really make sure that it's sending the compressed gradients across the network, and really test how much the throughput improves. So this one is in terms of epochs. So here you won't see an improvement because it's not the actual wall clock time, right? So this one is mostly to check, is it training well, and what is the test accuracy? So I didn't show the training accuracy here. In training accuracy, there's actually an acceleration similar to what Adam does, right? So compared SGD and Adam tends to train faster than SGD, and similarly we find for SIGN-SGD. So that's in the paper. And then for the test accuracy, what you see is there's almost no loss in accuracy, right? So even though, we don't have a generalization theory currently for SIGN-SGD, but in practice we are finding that it's not being affected too much. And so that's with the with the testing, and the other is the throughput, right? So here you see, so this is like 7 voting workers, so this is doing SIGN-SGD, and whereas this one is just the full precision SGD, and you can see like there is, it gets to train faster than if you want to reach this final accuracy, it's so much faster. And so that's the idea. And in fact, SIGN-SGD will get more advantage when it's bandwidth limited setting. So right now, we hardly train anything on the edge, right? So the edge devices can be like our cameras that are now having GPUs or having deep learning enabled. So we are not doing any learning, or our Alexa or our phone, everything is being sent to the cloud now. But in future, there may be privacy constraints, there may be, that's the federated learning. There's also bandwidth constraints. If you're having huge videos and you want to retrain your model, you can't, instead of compressing the videos themselves, it's better to train locally and compress the gradients and send them. So I think there's a lot of potential there to get even much larger gains than what we see here. But even here, it's impressive. It's about, I think, 30% in 7 workers and 25% on 15 workers on AWS. I mean, AWS has high-speed networks, right? And even then we can get this gain. And so the NICL is the state-of-the-art communication framework by NVIDIA. Now we've open sourced it. When we published the work, it wasn't. Okay, so let me finish this work and we can take a break. So that's the overall, so because we didn't have it open source where we published this is a black box, right? So we have no idea what happened, but in future we plan to now also chunk up what happened within the NICL framework. But what we find here is, so there is an additional computation because you have to compress it. Because you're taking now the signs of the gradients and you still have to put them into the tensors form, right? So in the compressed form so that it can go through the network efficiently. And so the major part is still the communication itself. So gathering and doing the majority vote is taking the most of the power, framework. And so as long as the communication is the major part of your algorithm, then it's SIGN-SGD will be very effective. And this is with SIGN-SGD, right? So with SGD, you can see potentially here a large part went into communication. And so we are also experimenting with many other networks. So what I showed you was ResNet 50. So that in fact has the smallest impact compared to other heavy models like this QRNN model is an NLP model, right? So with those many fully connected layers, in fact, you can get even a much more speed up by doing gradient compression. So the other aspect is about fault tolerance. So if you now have multiple workers, and if one of the workers or few workers get adversarial, right? So can you tolerate it? And with SGD, you cannot, right? SGD just the way it is, because if you're averaging and if one machine just sends it to infinity, you're done, right? So you just, if you're averaging, that's not robust. And so people have tried other means to limit that. And what we are saying is SIGN-SGD just by default has a nice fault tolerance feature. And in this case, I think this was where we show that if roughly less than half of the workers are behaving adversarially, as long as they're independently adversarial, we can handle it. We can still get the right we can still get the convergence. So, and this convergence rate is just suffering based on how many Byzantine workers there are. Right, so that's the other, there's a lot of details, but the main idea is there's fault tolerance built into SIGN-SGD because we're limiting the influence of any single machine. I have no idea why it didn't.
It could be different adversarial workers from iteration to iteration, right?
I think in this case, we assume they were fixed. It may go through, but we have to still think it's not clear. This one's for when you fix some of them to be adversarial. That was, I think even at 43%, it was still actually the accuracy didn't suffer a lot. So that's what this plot was supposed to show. I think something happened when I transferred from machines. Sorry, I don't know why it's not showing. But it's in the paper, so you can go and check it. But that was, again, showing in practice you can handle these adversaries. And so that's the main takeaway from this work that, the first thing was we asked theoretically what's the impact of gradient compression, right? So there were a lot of empirical works that tried to compress gradients, but we felt the theory was still missing. And the previous theory tried to get it to be close to the full precision stochastic gradient descent. And for that, you needed to do all these correction of quantization errors. You needed to make the gradients unbiased, right? We said, don't worry about it. Directly analyze what is the impact of just taking the signs, right? So these require different concentration bounds. But because it's the signs, it's Bernoulli and binomial variables, it's still simple enough that we can handle it in theory. But also in practice, we are seeing this nice match because what we are saying is there are fairly simple conditions we require it to have the same convergence rate as the full precision stochastic gradient. And the most important one is you don't have highly skewed noise. And in practice, we are not finding that. Right? The important thing is we are tuning hyperparameters, we are making everything sure to kind of discard all the bad scenarios for training and only taking the good ones. And there, I think it's fairly benign and these conditions hold. And the other thing was in practice, this does give us a big jump in performance, especially in the low bandwidth settings. So I can take some questions. Maybe we can take a short break and I can come back.
I have a question. Yeah. So if you compare, I mean, train to convergence with SGD and SIGN-SGD, are you seeing that they're converging to the same kinds of solutions?
So I guess how do you test that, right? How do you test whether two are similar or not? Because you can have all kinds of transformations.
That's true.
Right? So, and so that's the challenging part. There is, other than to look for test accuracy, there isn't a clean way to ask are they the same or not.
And theory-wise also, I mean, there's no guarantee, that the two are going to wind up in the same place, right?
I mean, there's no reason for that to be, right? Because the trajectories are very different. And that's why, as I said, we still don't understand generalization. I mean, we don't understand even in the standard SGD case. But here, it's still incomplete, but that's an open question.
Actually, the same question. Like, can we expect both of them to have same kind of implicit bias?
Yeah, again, this is something we've started thinking about, but I don't have I think it'll be different. I mean, for sure, it's different. The question is, is this still, the SIGN-SGD, is it still having, I think it still has some algorithmic regularization, right? So, I mean, it still has the impact of noise, but it's only taking the sign, so maybe that impact is reduced. But how is that affecting generalization? It's not clear. And the other thing is, you saw like in many of the experiments, the accuracy was same, but in the beginning, we had challenges, right? And that's because of the hyperparameter tuning. SGD has been so well tuned, and so we were just transferring the parameters from hyperparameters from SGD to SIGN-SGD, and then the performance was quite bad. And so that's why empirically it's so hard to say this, to be honest, because if you don't do full hyperparameter tuning, who knows, right? But that's when I told the students, no, burn more AWS, money, that's okay. And then the results really improved. So sometimes, that's why with empirical studies, there's so much we still find it hard to verify.
Also, so the idea of sign can be extended to any other algorithms, like sign Adam, sign move.
Yeah, I mean, Adam currently doesn't have concrete theoretical analysis, right? It's challenging. And so that's why I said SIGN-SGD is in fact a limiting case of Adam. So if you shrink the window of Adam to just one sample, right? So that's nothing but take the gradient and then divide by the magnitude of the gradient, that's nothing but the sign. So think of the SIGN-SGD as a limiting case of Adam. So Adam in general is very hard to analyze, but this gives us now a way to. And in practice, we found them to be very similar. So the signum, the sign of the momentum-based algorithm, if you also add the momentum term, we found it to have very similar performance to Adam in practice.
Thank you.
Connection between solving SIGN-SGD and solving SGD on a different problem formulation? Like, for example, like if I take a gradient and then compute the sign, then that's really like the gradient of a L1 norm instead of an L2 norm. Mm-hmm. I'm wondering, like, is it getting at some actual fundamentally better formulation, or is it really just an improvement in optimization?
It's not clear it's better, right? So, I mean, again, better in what terms? If we ask for convergence rate, then we have the two convergence rates. We can compare and ask when is one better than the other. But again, that's only a bound, and it's. But if you ask about generalization, that's a whole other story. So it's not clear. It's not clear.
I would like to ask, like, if you do more parameter tuning, so like right now you're considering the good scenarios, like would it be scalable to generalize all the scenarios, like good and all like bad as well?
Yeah, so all the experiments we've found so far, right, it's worked. I mean, we haven't had a negative result yet. I mean, in fact, in other papers, we've also published negative results. That's something I think as a community we need to do more as well. But in this case, we haven't, right? So there could be, I mean, of course, there definitely will be scenarios, especially if the data is highly biased, right? It has all kinds of, but then my guess is even SGD won't work very well. So it's hard to think of a practically relevant scenario where SGD will work wonderfully and then SIGN-SGD will fail miserably. I mean, you can, construct these kind of pathological scenarios like the one that was outlined in the Adam paper. But to me, that's, I can't imagine that in practice happening.
So in practice, do you think that this performance will depend on the batch size?
Yes.
Yeah, right. Because
so in practice, none of them were terribly large batch sizes. They were still, I think,
that happens.
1,000. Yeah. So, I mean, there have been a few papers trying to do very large batch size, and they're doing all these layer-wise adapting. There's so many other details, and I think that's a whole other question. I mean, there's no theory right now, right?
Exactly. Yeah, because
how we can adapt better.
Philosophically, it says so that it should depend on the batch size.
Right.
Yeah.
And that's why in our first work, because we made the large batch assumption in theory, we felt it was still incomplete. And in the second one, it's a much more detailed analysis, and the result doesn't look as pretty, but on the other hand, it's kind of getting to the similar rates. Great. Maybe we can take a short 5 minutes break and come back.